This lesson is for sections 4.1 and 4.2. We are now talking about transformations. So we want to identify the type of transformation that maps the unshaded turtle onto the shaded turtle. So you've probably learned these before in terms like flip, slide, turn, and now we're going to start to use more high school terms. So in this first one, even though it is a flip, I would call this a reflection. In the second one, even though it looks like a slide, right, it moved down, I would call that a translation. And this one looks like it turned, but we're going to call that a rotation. These three transformations are all considered congruence transformations, which means that the beginning picture and the ending picture are exactly the same. They're just located in a different place or orientation than how we started. In today's lesson, we're going to focus on these first two, reflection and translation. So we're going to start with translation. And translations can be written in words. They can tell you to move this many spaces right and this many spaces down. But the two main forms we're going to use are called vector form and function form. So vector form has these pointy looking brackets. They almost look like an ordered pair, but with points. And it is sort of an ordered pair because this represents how you're changing the x value, and this represents how you're changing the y value. So the example that they give here, the vector 7, 4, means I'd be moving 7 in the positive direction for x and 4 in the positive direction for y. Function form is written more like a rule, and we're going to have a lot of rules that we learn in this section, where they're saying if you started with a point x comma y, you're going to do x plus a and y plus b. Right? If there was negative values that you're translating, you would just have minus here instead. Right? But these are our two forms that we're going to be using. So if we have our triangle with its given coordinates, we want to translate along the vector 7, negative 2, and list the image coordinates. All right, so the image is the new picture. The pre-image is the old picture. So this one here is our pre-image, and now we're going to find the coordinates of the image. And we want to rewrite the translation in vector form. I'm going to start doing that because that's the easiest thing to do. So this is a positive 7 and a minus 2. So every point goes from being xy to x plus the 7 and y minus the 2. That's our function form. That part is done. For the other part, you can either count the spaces on the graph, or you can actually do the math to each of the ordered pairs. Since we're going to be graphing it as well, we may as well count the spaces because that's going to help us anyway. So let's start with this point x up top. So I'm going to go 7 to the right. So I'm going to count 1, 2, 3, 4, 5, 6, 7, and then 2 down. 1, 2. And now I have to figure out what I'm going to name this point because it can't just be x again, right? It has to be something different. So the image is going to get a little apostrophe on the variable. It's not the right word. On the point name. And we're going to call it the prime. So this is x prime at 4, 4. If I took w, went 1, 2, 3, 4, 5, 6, 7, down 2. We can call that w prime, and that's at 4, 0. And then y, 1, 2, 3, 4, 5, 6, 7 to the right, 2 down, is at 7, negative 3. And now I have my image. Here's a try problem if you'd like. You can pause. Answers are posted online. So my next example, I'm given the coordinates of both the pre-image and the image. I know these are the image coordinates because they have their primes on them. They want me to write the translation vector. So I want to know how did I get from 3, 2 to become 10, 5, right? Because f went to f prime. So from 3 to 10, we increased by 7. So the first number is going to be a positive 7. And then we increased from 2 to 5 by 3. So the second number will be a positive 3. And that's our translation vector based on this pre-image and image. Here's another try problem. Pause if you'd like. The answers are posted online. So now we're going to talk about reflections. So a reflection is where you're using a line to basically create a mirror image. All right, we call the line we're flipping over the line of reflection. Every pre-image point is the same distance away from that line as the image point is. The only difference is if the pre-image point started on that line, then the image point stays in exactly the same place. There's no place for it to go. We also always move towards our line of reflection at a right angle. That will mostly be important later on when we flip over some diagonal lines like this. For now, though, we're going to talk about different rules because there are 4 specific lines that have rules that we could apply to them, and we don't actually have to graph them to figure out what the new points will be. So the rules for our specific reflections, the x-axis, the x value will not change, but the y will become the opposite sign. This is not saying that it automatically has to be a negative number. It just means if it was positive, it becomes negative. If it was negative, it becomes positive. It goes to the opposite. For the y-axis, the x will change its sign, while the y remains the same. For the line y equals x, we flip them around, so whatever was originally in the y spot becomes the x, and whatever was originally in the x spot becomes the y. And for the line y equals negative x, it's the same as y equals x, but now we slap some negatives on both of them. All right, in case you're wondering what the lines y equals x and y equals negative x looks like, they are diagonal lines, but they are specifically through the origin. So this would be the line y equals x, slope of 1 through the origin. And then this would be the line y equals negative x, slope of negative 1 through the origin. So for example 3, I want to list the coordinates of the image after doing a reflection over the line y equals x. That rule that we just learned is flip them, y comma x. So m prime, instead of 6, negative 2, would be negative 2, 6. N prime, instead of being 5, 2, would be 2, 5. And p prime, instead of being 1, negative 7, would be negative 7, 1. And that's all there is to do for that. Example 4, same idea. We want to reflect over the x-axis. So if I know my rule for x-axis is x negative y, or x opposite y. Q prime, not changing the 0, but the 9 is going to change to the opposite sign. So 0, negative 9. R prime, not going to change the 4. And here, if I try to change 0 to the opposite sign, 0 doesn't have a sign, so 0 is going to stay. What this tells me is that this point was on the line of reflection. It did not change. And then S prime, I'm not going to change the negative 1, but the 3 will now be the opposite sign. So here's a try problem. All right, if you'd like, pause. Answers are posted online. For example 5, now we're going to reflect over a line that does not have a rule that we can use. So we do have to graph this line. And if you remember our lesson from chapter 3, we know that anything that's x equals is going to be a vertical line. So if I go over on my graph to where x is 3, I'm going to draw a vertical line there. All right, it's really important that you draw this line for yourself so you can count the number of spaces away each point is. Because when we first learned about our reflections, we said that however far the point is from the line, we're going to do the same thing past it. So if C was 1, 2 spaces away from this line of reflection, we're going to go 1, 2 spaces away to put C prime. So that's at 5, 3. For B, if I count 1, 2, 3, 4, I can now count 1, 2, 3, 4. And that looks like it's at 7, 5. And then A, 1, 2, 3, 4, 5, 6, 7. We go 1, 2, 3, 4, 5, 6, 7. If it went off the graph, that would be fine, as long as it didn't go off by a lot. I'm not going to give you anything that goes off by more than 1 or 2. If you went off the graph by a lot, then the problem is probably with something you did. So here's 10, 2 for our A prime. All right, here's a try. This one is with a horizontal line because it is y equals negative 1. So if you'd like to give it a shot, pause. The answers are posted online. So now we're going to reflect over the line y equals x minus 3. So this is a diagonal line, and it is not the line y equals x. So we actually have to figure out where this belongs on the graph and graph it. So if this is in slope-intercept form, the intercept, the y-intercept is negative 3. So I'm going to start on the y-axis, and I'm going to go down 3. And my slope is a positive 1, which means I'm going to go up 1 and to the right 1. Up 1 and to the right 1, because it's 1 over 1 is my slope. I hate when that little box appears. And I'm going to keep drawing those dots. All the way. And I'm terrible at drawing straight lines, so I'm going to try to use my line tool here to do it. There we go. That looks perfect. So if you recall, we said we always move towards the line perpendicular to it. So if I was making my slope up 1 to the right 1, then I'm going to count down 1 to the right 1 to get to that line. So if I wanted to reflect G, I'm going to go down 1 to the right 1, down 1 to the right 1. So that was 2 spaces of down 1 to the right 1. So I'm going to do the same thing past it. 1, 2. So it looks like it puts us at 5, negative 2. H is only half a space away, so I'm only going to go half a space away. So that's going to be at 8, 4. And then I, counting diagonally, 1, 2, 3. So we're going to go 1, 2, 3. So that's at 10, 1. All right, and that wasn't terrible either. So that is our reflected image. Here's another try problem. I would really recommend trying this one if you can. Pause, and you could check the answer online. Symmetry. So symmetry is when a rigid transformation is another word for congruence transformation. Another word is isometry that we could use. They all mean the exact same thing. Symmetry is when a rigid transformation can map a figure back onto itself. So when you perform the transformation, it still looks exactly the same as it started. We're going to talk today about line symmetry. So their definition is if a figure can be mapped onto itself by a line of reflection, which makes sense. I like to think of it as, can it be folded in half? So can you fold it in half? And I'm talking exactly in half. And whatever happens on one side, it should be the mirror image on the other side of that line that we're reflecting. If they're not the same direction, if they're not the same length, then that is not a line of reflection, or it does not have line symmetry. So if I look at these examples, I want to determine if it appears that they have line symmetry. Sometimes you have to actually try to draw the lines to determine if you think it has it or not. So here, the most obvious way, it looks like this. And it does look like we have the same exact thing on both sides. So there's a line of symmetry. But this star has 5 equal points. So it makes sense that I should also be able to go from any point to the indent across from it and form a line of symmetry. So this picture actually has 5 lines of symmetry. So when this says state whether it has, yes. If yes, draw a line of symmetry and state the number. So there are 5 lines of symmetry in this star. For the heart, again, looks pretty obvious that we can go this way. So there is at least one, but it doesn't look like I do it anywhere else. So this is just going to be that single line of symmetry. It doesn't change the fact that it has line symmetry. There's just less lines that work. For C, the most common way people go for this is they go diagonally this way. But then if I look at the piece over here and the piece over here, this one is much longer than this one. So that line doesn't actually work as symmetry for us. And if we tried to go maybe the other way, again, this one much shorter now than this one, so that line doesn't work either. And if we tried to maybe go this way, they're the same length, but they're not going different directions, right? If that's kind of going like that, that should have been going a little more down like that to be considered symmetry. So this figure does not have line symmetry, right? It's fine if a figure does not have line symmetry. There's no way we could fold this picture onto itself. So here are the last 2 tries. If you'd like to do them, their answers are posted online, but that is the end of 4.1 and 4.2.